Now we want to discuss the concept of a differential. And I just want to sort of motivate this a little bit. And I begin by saying from the work you've already done with computing derivatives by definition, you should be familiar already with the idea that the slope of a line between a point um, on a curve, say this point P, and a second point Q, the slope of that line approaches the slope of the tangent line, this one in red, as the 2 points P and Q get closer and closer together. That was sort of the motivation of the limit definition of a derivative. So you should be familiar with that idea. Symbolically, we'd say that the change in y with the change in x. The change in y is this distance right here. That's how much y changed on the line connecting P and Q. Divided by the change in x, that's the amount of change between the x-coordinate of P and the x-coordinate of Q. So the change in y over the change in x is approximately the same as the change in the, looking at the tangent line, how much the y changed over how much the x changed. So symbolically, we'd say those two slopes are approximately equal to each other as long as the points P and Q are close together. And also, just sort of as an aside, dy over dx is the derivative of the function with respect to x. So the slope of this tangent line is given by dy over dx, or f prime of x. And one more thing I'd point out here is that unless P and Q are on top of each other, in other words, as long as they're actually distinct points, dy and delta y and dy are going to be different from each other, although they will be close together as long as P and Q are close together. However, delta x and dx are the same thing. That distance doesn't change whether you call it delta x or dx. It's the same for the tangent line and the line between P and Q. Now, taking this right here, if we take it literally that dy is actually a change in y and dx is a change in x, we can actually treat these as two separate quantities and multiply both sides by this dx. So that's sort of the idea of a differential, that we take seriously the idea, whereas earlier we had a symbol dy over dx standing for derivative. We take the idea literally that dy is some small quantity and dx is some small quantity, and we can actually work with them. They're non-zero. So if I do that, I end up with dy is equal to f prime of x dx. And in this context, dx is going to be a small value of x, in other words, the change in the x's, and dy is going to be a small value associated with y, namely the change in the y coordinates for the tangent line. Now that is the basis of the definition of a differential. So formally, here we go. For a function y equal f of x, whose derivative exists, the differential of x, which you write dx, is an arbitrary real number, and it's small compared to x. And the differential of y, written dy, is given by this same equation I generated over here, namely dy is equal to f prime of x dx. And again, to emphasize, for our purposes, the usefulness of this result lies in the fact that as dx gets close to 0, in other words, as P and Q move closer to each other, dy is actually a good approximation of delta y. Let's jump right into actually doing a simple differential just to get our feet wet. Suppose I ask you to find dy if y is equal to 6x squared. The first thing you do is apply the formula. dy is equal to f prime of x dx. So this is your f of x. The derivative of 6x squared is 12x. And then the dx is just along for the ride. So the differential dy is simply 12x dx. Now I might ask an additional question. For example, I might say, what is dy if x is equal to 2 and delta x is equal to 0.1? So the differential is here, but if I tell you particular values of x and delta x, then I can calculate an actual numerical quantity for dy. And also, I'll say this again, although I've said it before, dx and delta x are the same thing. So again, going all the way back to the original diagram, dy and delta y are close but not equal, as long as p and q are distinct points and p and q are close. But delta x and dx are the same thing all the time. So the fact that I've got a dx up here and a delta x down here doesn't really matter, because what I know is that dx is the same thing as delta x. So that's the first thing I'd say. And otherwise, you just plug the values in. So I take 2 and put it in for x in the formula for dy, and I take 0.1 and put it in for dx. So if x is 2 and delta x is 0.1, then dy is 12 times 2 times 0.1. Now I can do this probably just in my head. 12 times 2 is 24, and 0.1 times 24 is 2.4. And if you don't believe me, you can take out your calculator and double check me. We also use differentials quite often in application problems. So here's another example that I want to end with. It says the profit in dollars for a small company from the sale of X ovens is given by P of X equals 4,000 times the natural log of X. The sales estimate for the year was 1,000 ovens. And our instructions are to use differentials to approximate the change in profit if only 900 ovens are actually sold. So the estimate for the year was 1,000, but actually only 900 were sold. So the first thing you do is look at the profit function. And realize they're asking us the approximate change in profit. So they want us to find dp. Now notice that we were using x and y before, now we're using p and x. It doesn't matter. So dp, according to our definition, we're using a p instead of a y, that's the only difference, is f prime of x dx. And if we actually plug in the derivative of this function, actually I should say the derivative of this function is 4,000. Remember, the natural log of x, the derivative is 1 over x. So you get 4,000 times 1 over x, and then you've got your dx. So you end up with dp being equal to, now 4,000 of course is like 4,000 over 1, so you got 4,000 times 1 is 4,000 over 1 times x is x times dx. Now think about this a minute. They're saying that we were expecting x equal to 1,000 ovens, so that's my value of x. But I actually only got 900. That's a decrease of 100. So what they're telling you there is that we were expecting 1,000, got a 900. So what they're telling us there is that delta x is negative 100. And remember, delta x is the same thing as dx. So by saying that we went from what we expected was 1,000 down to 900, they didn't actually tell us delta x, but it's easy to see that that's a decrease of 100, and that negative sign is important. So all I need to do to find the approximate change in profit is plug in 1,000 for x and negative 100 for dx. So I get 4,000 divided by 1,000 times negative 100. Now, I'm not going to make a big deal about the arithmetic, but 1,000 goes into 4,000 four times, and 4 times negative 100 is negative 400. So the change in profit would be about negative $400. So the profit estimate that they originally had would have to be decreased by about $400 if they actually only sold 900 ovens. And that's the idea of a differential, the concept, and also a couple of simple examples of how it's actually used in practice.